1982. Then after spending 2 years in the Mazu, okay, a very nice place. Okay, so he went to Canada in 1985. Connecticut. Oh, sorry, Connecticut. And he obtained his PhD in 1992. Right? Yeah, in the University of Wisconsin. Afterwards, went back to Academia Sinica, Taiwan, and to do his research. Now he's the researcher of in the Academia Sinica. Although he studied physics, but his research is very it's not the same as us. So today he's going to talk about this whole brain mapping with X-rays. He's an X-ray expert in Taiwan. So let's welcome Dr. Hwu.
So a nice introduction. Okay, first, okay, 各位学弟学妹好 ，okay, 各位老师好。As I introduced, my training is all in physics, so I think I'm very happy to have a chance to talk to our fellow physicists, so that I can make all my insults to biologists. Yeah, this title, okay.
闭上麦比较没有那么有声音。
was introduced. Yeah, X-ray was what I spent my lifetime of
这个是电子讲座，
career.
因为它比较稳定，就是我不太敢用演讲设备。
And at that time, I already know that Taiwan is building a synchrotron, so I thought, why not? So I joined the group to do synchrotron. But when I started, we're doing something as a physicist really much more fascinating. For example, at that time we do, like Professor Yeukuang Hwu did, we're doing strongly correlated system. My thesis work is about high DC superconductors, observing the first time the gap opening by photon-emission spectroscopy. And then one day I received a phone call from our former director, Zheng Genzo, calling to the lab, and asked me what was my plan. I didn't know he's calling to the room. So in the very noisy conditions, I picked up the phone on the wall, and then he was telling me, are you interested to get a job in Taiwan? I said, I may. And he asked me, do I have any other offer? I said, yes, some postdoc somewhere there. He said, come back, we'll offer you a staff position. That's how I did it. So since '92, I moved back to Taiwan, and then at that time the synchrotron is not ready. So I spent 2 years, again, wandering around the world. Finally, and when the synchrotron is ready, I started there. So my career is, as I said, it's quite simple. You know, from '92 and then all the way now is academia syndicate. And then when I come back to Taiwan, I was tempting to do the same thing like for the mission. But then I started to realize that we did not have all the advantage. For example, at that time you compare to the Shen's group, and then we do not make our own sample. And so I decided at that time I want to do something more useful, practical. Okay, so I started with microscopy, and because of microscopy, and then in the synchrotron, the natural choice is using X-ray. So we started X-ray microscopy, and but when we started, I was already attracted by biology, you know, because I realized, you know, something fascinating like a strongly correlated system, which is really intellectually challenging. But on the other hand, in terms of the broad impact, at that time already, that was more than 20 years, I thought, but there's a lot of things for physicists to do. And it took me almost 20 years to convince biologists we can do it, we can do something for you, and we can be probably even better. Okay, so, and then, to challenge biology, actually, this is the biggest, actually, a lot of people, for instance, one time the Science magazine run a list of what's upcoming big science, and then understanding brain is one of the, they call it final frontier. So that's the chat first, okay? And I will start, this is my collaborator. You can see I cannot differentiate them anymore because many of them are really lifetime collaborators. So I build my collaboration basically based on friendships. So when you have friendships, you collaborate whatever you're interested in. So that's why I cannot remove, so you have to accumulate these many years of things. But what I highlighted are the one probably directly related to the X-ray microscopy and the instrumentation. Okay, the other, they provide sample, provide their individual specific science to us. Okay, and then you can see it start from Taiwan, Japan, Korea, China, Singapore, and so on. And then that related to the second part of my project to introduce, you this international project we organized, which is one of the very ambitious things in trying to map a human brain for the first time in Okay, oops, sorry. Well, this is my group, so again, I'm not going to spend the time to say that, but basically my research is really focused around X-ray, but on these 4 separate subjects. First, we're developing X-ray microscopy as the instrumentation, as a technique. And then, because of X-ray microscopy, we have to do the nanoparticle synthesis, and it turns out I'm using X-ray as well, which is, again, a little bit unique, but I'm not covering that. But the reason to do X-ray nanoparticle synthesis is, again, for the need of X-ray microscopy. And the fabrication is even more direct link because we need optics, which the one we use is called Fresnel zone plate, and which is one of the most effective way to focus X-ray. So it's the best, most effective, efficient optics for X-ray. If you can imagine X-ray, if you want to do any manipulation, you cannot use a regular lens like optical microscope because X-ray just penetrates and then the refractive index is so small compared to 1. So that's why we need a special device. And it turns out that it's fortunate our institute had at that time had one of the best electron beam writer, so enabled us to make this device, which actually created the very basic advantage, or we can claim in this X-ray microscopy business. And then again, because as I said early on, I was already attracted by biology, so I was trying to make use of the X-ray imaging for bioimaging. And that's also one of the more tricky reasons is, it's not saying X-ray imaging or microscopy is not useful for material or physics or chemistry, but rather, I said if I have an instrument which is give you a very good resolution, very good performance, and then I open to a material scientist or physicist, they know immediately what to use for. So they can come in. I do not even need to supervise them or coach them to do anything. But for biology, my early experience in academia sinica now is probably safe to say is dominated by biologists. So I knock almost everyone's door telling them we have this wonderful technology coming, would you be interested in? They all tell you, okay, wait till you get it. Okay. So that's why in this biology collaboration, I have no one from academia. Okay. The reason is because they are so wealthy, they have everything, and they are all busy with what they have already. So they have no time to work with you to explore something new. Okay. So this is my sweet revenge to them. I'm going to do something that you cannot do with your existing instrument. Okay, this I would just use it, try to justify why physicists is useful and important. But I think you know very well. But basically, you can see laser confocal, and then the Nobel Prize in chemistry. Of course, these are physicists, okay, on the super resolution work, okay, and then protein crystallography. Again, this is starting from the early X-ray crystallography work, and then plus the synchrotron radiation, and that's now for almost 2 decades is a dominant in this field. And actually, single-handed problem is protein crystallography, structural biology, and now also prior electron microscope. When this comes up, and that's almost replacing the protein crystallography. And this again, all the early development is done by physicists, and even including how to prepare the crystal samples, the biology sample. Okay, and then in back to X-ray. Okay, I will list. Okay, in my view, the view of the important breakthrough in X-ray imaging is not X-ray. X-ray imaging is first in the early 90s that people introduced the idea, demonstrate how it can be done by phase contrast. And this is again nothing new. The phase contrast, probably next week, is very simple. It's difficult to realize with X-ray for certain reasons. And then with the third generation synchrotron, which we call it, this means the synchrotron start from the 90s, and it becomes feasible to do it, and then take advantage of it. And the phase contrast, the primary use is actually for soft material, okay, so biology, polymers, and so on. And then the other thing, we are heavily involved. We are not the one initiated, or I can even claim we're the one making the best contribution, but we're part of this development is the get the nanometer resolution. Okay, and this one we think will play a much more important role. And then naturally, X-ray, if you couple it into the spectroscopy aspect, you can have a very good elemental contrast, which is able to tell. But that's mainly for material because of biology. The elemental contrast is very limited. And then this is something I would say I should put a question mark, but then the high speed. And then the whole message I want to show you is actually speed is what enabled us to do whole brain mapping. Okay, then this is a standard advertisement for X-ray and the synchrotron. And since the discovery in 1895, and for more than half a century, it stayed reasonably the same. Until, rotating nanos started in the 60s or 70s, it stopped picking up, but really the breakthrough is the introduction, the first generation synchrotron. From then on, you can note that this is a logarithmic scale. So from here, it's very fast growth. And now with the new breakthrough is called X-ray free electron laser. You can imagine that this is another 12 orders of also magnitude increase in terms of brightness. Brightness, we conclude that is the most useful parameter or characteristic of X-ray science. So this is generally a very good indicator that you can see. And then we often argue this is probably faster than Moore's law in terms of the growth. And some of the synchrotron community scientists like to honor ourselves, say this is probably perhaps the fastest growth in any technology. Okay, which again I think is just a trick of you do the calculation. All right, but still, same thing to compare. So there are a lot of things that we cannot do. So when I go to give a talk in a medical hospital and so on, I usually tell them this is not the X-ray your grandpa knows. Okay, this is the X-ray you probably never heard of. Medical doctors like to know like to think they know X-ray. They use X-ray almost daily, right? But I tell them compared to what the resolution you have achieved now with the X-ray radiology, which is hundreds of microns, and we are now to the 10 nanometer resolution. Okay. And phase contrast, to put it very simply, is just basic is like a lens. If you go through something with a different refractive index with the boundary, you deflect the beam, and because of in X-ray, these absorption shows probably very little contrast if you have a similar material. But with a phase with a different refractive index, you will see a fringe. So if you realize that in other things like this is a case, this data already obtained almost 20 years ago. This is a cross optical fiber, which is silicon. And then you can see there are different layers. But this, I put it here, is the distance between your detector and then your sample. And you can see when that increase, just like when you go to radiology, if you go away from the detected plate, you can see things start showing very much. And that's to explain it to physics. It's very simple. You have a refractive index difference, so the beam is deflected. But this angle for X-ray normally is very rare, 1/1000th of a radian. So you have to move it really far away to expand this angle to be detected by your limited resolution detector. But the problem is why it doesn't show or use before, because when you have a very poor X-ray source, just like the light source here, you can look at your shadow. It's very blurred. But if you close it in, then it becomes sharp. This is a simple geometrical reason. Right? So, but in order to get these very small fringes, you have to have a very good source. So that's exactly what we call the brightness, because if you have a very, very small source, like when you look at the shadow from the sun, it's much sharper than this. Yeah, even though you say, okay, the sun is so big, but they're so far away. So in this case, you can consider it's almost like a point source. This edge blurring due to the size of the source is much more reduced. So because of this refractive index created fringes so narrow or so small, so with the limited resolution of your detector, you have to pull it very far. But then if you have a very bad source, your edge is blurred and you wash away all these enhancements like this. Okay, so this is the case. When you go very far, you see things become blurred again. Okay. So this is simple demonstration. But then you can see that gives us an opportunity to observe. For example, we go to radiology. You usually see bones. The doctor would mainly use it to see bones. And maybe now in some cases I can see the watery portions of your lung if you are infected by virus. But other than that, these are all based on absorption. This means X-ray go through, the electron density of this material is higher than the rest, and it absorbs more X-rays. So if you image that, it gives you the contrast. But when we use a phase contrast, that I will not cover today because it's not so much relevant to the thing I want to tell you about brain mapping. But it gives you open up opportunity to look at soft tissue. For example, we have a side project trying to collaborate with industry to develop a new generation X-ray source, which is not targeting for high resolution, but rather better resolution currently that will allow you to see the baseline. In this case, we have demonstrated using mouse model. You can see actually the thing on the alveoli. You can see individual alveoli. And then you can see these are all soft tissue. If you look at regular X-ray, it's all blank. And then because of phase contrast, you can see a fringe, you can see each individual circle, for example. So we have also demonstrated that it's very good to look at the tumor cancer. So we can use it as an earlier diagnosis for cancer, for example. Okay. And then if this thing goes well, then we really claim that we can replace all the X-ray source now you see in the hospital, including CT, radiography, and then provide you additional contrast information. Okay, the second one is the nano resolution, which is, I said, because of the detection of X-ray is difficult. You can imagine that, X-ray, first, how do you detect it? That in the old day we have ion chamber or something. Then if you want to do imaging detecting. So now the best one is still using CCD or CMOS camera. But then it doesn't detect X-ray, so we have to use a conversion. So this is not right. We use a scintillating material. So in scintillating material, it's just your TV screen. If you hit by X-ray, it gives you optical light, visible light, and then you image that by camera. But then the resolution, you see the smallest, even nowadays, smallest pixel of a CCD is probably 3 micron. So if you image X-ray directly, like a radiology, like put a plate on the back, the best resolution you can get is 3 micron. But you know the X-ray's potential is much better than that, because if you judge by its wavelength, it's 1 angstrom or small. So in principle, you do protein crystallography, you are actually getting atomic resolution. And why you cannot image that? Because you don't have a detector. For example, if you have a detector which can actually differentiate every pixel with a 100 nanometer pixel size, you already have a 100 nanometer resolution X-ray image. Just because of that difficulty, so we have to use this. And then the other way to do microscopy is you magnify your image. And again, X-ray is quite difficult to do that. So the only few really effective optics, we call it, this one is tested, we call it Fresnel's only. Basically, you made this in your optic course, you will always saw that. Actually, you can see this device quite often, like in the back of a bus. You see that in the back window, they put this a big thing, or you have a magnifier made of long plate. So if it can be used as a magnifier, it's a lens that you can use it for, and then it turns out it works still with X-ray because it's a diffraction optics. So we use the X-ray optics, put it in the backfocal plane to image the X-ray image created by the X-ray source. And then you magnify it 200 times, 1,000 times, and then capture that with convert it to visible light and capture it with the CT camera. So all the other are just optical design so that we can make the most efficient. But the key point is you have to have a magnification device. And that's where we started. Okay, actually, when the first time, I think in 2005 or 4, when I first applied for the National Nanoscience Program, and I was asked, I proposed to do this, and after a few years, we were able to make, using electron beam writer, to manufacture devices which has smallest 20 nanometer dimension, and then with the high aspect ratio, the second number is the height. So basically, we're building, these are all walls of more than 20 times the aspect ratio. And you know, this is not easy. So we are quite proud to say that. That's why we are the first one to get to this benchmark. And then we also made more commonly used 40 nanometer outermost zone. This zone you can see is in the middle, it's big, and then it goes smaller and smaller. So at the end, this is where it defines your resolution. So if we have 20 nanometer outermost zone, almost by the rule of thumb, you can calculate their resolution. Theoretical resolution is about this. So that means we have to put, if we want to get good resolution, we have to continue to push this smaller outermost zone. But on the other hand, because we're dealing with X-ray, so to create enough phase shift, that you need to have a thick enough, even using gold, we need at least something like the order of micron to have create enough phase shift so that by the end, it can create enough path difference to have constructive interference of X-ray. So this is almost cannot be compromised. And then you have to improve this, so that gives you this odd structure of very high aspect ratio, which has tons of mechanical problem, synthesis of process fabrication problem, and so on. And we're very happy that with the help of the project, we get to this. And then we use it with microscope, like I showed the outline before, the line sketch before. Then we are able to image a device, which is also we made, because making this kind of test pattern is already difficult. So we made the one ourselves with the inner most spacing is about 20 nanometers. And you can see this is reasonably resolved. And then we have made other kind of device, which is multi-layered structure, and then we cut it into a test pattern like this, and you can see this is 25 nanometer spacing, and then 20 nanometer spacing, this is 15 nanometer spacing. You can still see good enough modulation of intensity, so you can argue that our best resolution is roughly already on 15 nanometer. And this is, may sound trivial, but we have to say, when we start this project, the X-ray microscopy, the resolution is more than 100 nanometers. Why? Exactly because of difficulty to make this. So from 100 nanometer on, 60 nanometer, 40 nanometer, 30, 20, we are always the first one to demonstrate this. So we have a string of publication, which is kind of shameful because looks like all we have to do is changing the resolution numbers. So, the first 60 nanometer X-ray microscopy demonstrated. But yeah, this is I think this is, in a way, is how to get our name. Okay, because otherwise, everything coming later cannot be happening. So with this kind of microscope, we demonstrate this. This is a cultured cell. So to start, we did not know much, so we just take a cultured cell, and then these particles, these are gold particles. So endocytosis into the cell, and you can see them individually, not particle across the individual. Okay. So this is the size of cells. I don't need to make so much specific mark. And then this is the elemental, which is.
So what's the resolution then?
That one is already 20 nanometers.
20 nanometers.
Yeah. Okay. And then this one is to show just one picture. We have a paper published by collaboration, and then just to show, looking at the one of the electrodes, and then try to look at this three-phase structure, nickel, YZ, and then by focusing on the nickel absorption edge, you can actually create a contrast which is just due to the nickel itself. Okay. And this is also a very good resolution. This is about 30 nanometer resolution. Okay, this is done. Oh, sorry. Oh, the third thing I would like to say, which is, unfortunately, Taiwan decided not to build it, which is sort of disappointment. But we involved with the Japanese free electron laser, and then this is going to open again. I told you, compared to the peak brightness or brilliance of X-ray, this synchrotron compared to synchrotron, it offers 12 orders of magnitude increase. So you can imagine that 12 order magnitude can be used in a lot of places. For example, one example, when they proposed the synchrotron, the idea is to do protein crystallography, determine protein structure without a crystal. Because then you can actually image one single molecule, and just by the diffraction of its local electron density, that you will be able to convert back to its real space structure. And so in this case, they imagine that in the future, you put a protein in a solution, just spray into the beam, then you get the structure solved without. But unfortunately, this has become questionable because of the cryo-electron microscope come up. And this is, first of all, physicists still fail to demonstrate that. At the end, now to do single molecule protein crystallography, you require the flux is still probably 4 to 6 order magnitude higher than what it can achieve. So we physicists, the only way we said, we believe we can do that, give us time and more money. Like energy physics, we can always get there. Okay. But unfortunately, in the real application, you have a competitor, and then a private EM, now everyone can have that and do it at home. So in a way, that is a tough competition. But still, in terms of technology improvement, this is definitely a wonderful breakthrough. Many people believe that the inventor of the design of the idea of free electron laser would get Nobel Prize sooner or later. And this is all, I borrowed this from Spring A, so it just show all the possible application and how you do that and so on. So, and one of the typical examples I show you is that when you drop this is a very intense beam from the free electron laser. You drop this, these are individual molecules. You drop this into that, and then you capture that by big detectors. And by this diffraction pattern, you can reconvert back to this structure. they are even worried about, because in this case, in the protein crystallography, they have to put the sample in the prior state. And the reason is radiation damage. So that was actually the Nobel Prize to say, oh, to cure the radiation damage, we make ice out of it. And that is Nobel Prize. And then after that, everyone is using, because of radiation damage is really big in this case. So you say, okay, now you got 12 orders of magnitude brightness. Then what do you do? And then they even run a simulation, say, oh, within 50 femtoseconds, the protein likely remain. This is a simulation of that. Say, after this, I think this is 50 nanometer. So if you shoot by 10 nanometer pulse, you can remain intact and so on. But if you go longer, the whole thing explodes. And very simple, is you charge every molecule, every atom, and it just the Coulomb repulsion is enough to explode it. So this is why they say, okay, they have a code name. This is called detect and destroy. So basically, destroy everything. When we do this free electron laser experiment, you can see we put a sample into a liquid cell and with a seal membrane, but the XFEL can actually penetrate break the whole membrane, and sometimes even damage the complete silicon substrate. So basically, we just say, okay, we don't care if we kill, but we capture the image first. Okay? So this is a few examples we did. Actually, the sample was we used this liposome. It's a drug-containing liposome, so it's a liquid bubble, and with the size of 100 nanometers. By looking at this diffraction, and then with the help of theoretical development, we are able to convert that into, for example, real space image like this. So this is one liposome. Again, you see it's not exact, it's not very round, but we argue this is because of resolution. And by this, you convert this kind of pattern into this real space structure, and then you can see the size. This is 100 nanometer part, and you can count. And then the interesting thing is this is particle by particle. So we measure individual particle shot by shot, and then this. So it means this statistic of the size distribution is really by different numbers of image. So this is, okay, so with this resolution, we can even tell, okay, that some of the samples, these are, like this one is converted by this. So actually we have two particles nearby. So that create this oriented pattern. And then by looking at the intensity distribution, we can do similar thing by small angle scattering. And using this kind of thing, we can also estimate the size of the particle. And this is a cryo electron microscope image for the comparison. Okay. So, okay, and then also the one of the subject we use X-ray imaging, which is away from now the high resolution. Now we're going back to micron resolution, which is, again, I said, is 100 times better than mathematical imaging or CT. And this is in collaboration with the French team, which they provide this animal model with cancer. But this is specific is brain cancer, glioma. The reason is brain cancer is one of the most lethal. So many people die from that because there's really not so much cure. So we're interested to study the angiogenesis process related to the cancer, and then we choose brain as our animal model. Okay. So first of all, this is the X-ray image of a complete mouse brain, and here we show its vessel. So this vessel shows up not because it's not because of the phase contrast I mentioned, but because we inject a contrast agent to create a contrast, and this contrast agent is going out of body. Because we try to use, when you go to the hospital, if you are unfortunate enough to have the radio angiograph, so they typically inject this iodine containing, so they have a video, so it's not a shot, so they have a movie watching you. You can see this contrast agent flow through your artery, and then they can determine which artery is clogged, so they can put a stent and so on. And the same idea, by using this contrast agent, when we get to this resolution, it doesn't have much contrast. So instead, we have to develop our own going out particle as a contrast agent for injection. And then you can see inside, and this is, we claim this is a complete angiograph. because it gives you, by our resolution, it gives you the smallest vessel. The smallest vessel is about 4 microns. So it cannot be much smaller because you need to allow a red blood cell that needs to pass through. So even by squeezing, so if the inner diameter of the vessel is probably about 4 microns, or 3-4 microns. So with our resolution and with the sufficient perfusion in this particle into the brain through the vessel here, then we are able to image that, and this will be our first example of showing how to do whole brain. And then look at the individual thing that we learned, for example. These are the tumor that our collaborator created in the brain. So there's a selected specific kind of cancer cell. It grows into one solid tumor. It doesn't spread out too much, but it's one solid tumor. And then look at these 4 images, and they look quite similar. But if you look at the scale bar, so this is quite different. So we started with this. The idea is we want to use this angiogenic genesis or angiograph as a marker. So for example, one of the problems to operate a brain tumor is when you go to hospital, when you are diagnosed with a brain tumor, and then the surgeon wants to remove that. But handling brain is not that easy. So you cannot cut too much. You cannot use a spoon and cut out too much of a brain because you create a vegetable. Tricky part is even the medical doctor consider that's a success operation. If they don't kill you, it's a success operation. Okay, but then you see you create a vegetable. Okay, but if you cut it too little, if you did not clean it, and these things will metastasis, it will spread out, and it become much more lethal. It will defy your radiotherapy. So you become radiation hard, radiation resist, and you cannot use chemo either because they are trained or they are better. So then we thought, okay, if we use this, because angiogenesis is a hallmark of cancer. Almost every solid tumor, except like leukemia, these kind of blood, every solid tumor comes with angiogenesis. This is a natural process because cancer is a fast-growing ill cell. And when it fast grows, then you need a vessel to come in to supply its nutrients and so on. So this is coming almost direct correlation. So we thought if we can image this, that will give a surgeon, for example, a very good marker to say how do you cut on that. But when we studied that, we said, oh, we want to go in mouse. Yeah. Of course, in a human, we will have to do but then we find out, we want to say, okay, we want to do early diagnosis. So we try to make a smaller tumor. But then by continuing reducing the number of cancer cells and making it earlier, we find out no matter how early you go, this is only probably 2-3 days after you inject the cell, cancer cell into this specific region, it's already, they call it a switch on the angiogenic process. Angiogenic means, okay, so we are making an analysis, a military analysis, like when you go to want to land, like Normandy's landing, you want to create a bridgeport. So when you inject all these cancer cells, once it occupies the place, first it will be almost clean, almost 100%, 99% by your immune system, and immune system or whatever, defense system. But whoever remains, the first thing they do is they group together, and then they start calling to grow and then calling supply. And this new vessel, angiogenesis means vessel generation. So this new vessel they recruit by sending some strange fake signal to the body to send them the vessel to supply. And so the conclusion of this research is quite interesting, is that we are not able to people used to think angiogenesis because of hypoxia is the cancer cells dying because of they grow bigger and bigger, and oxygen perfusion and all these things become difficult. So they have to call in this. But this tells us actually it's probably not, because our collaborators say this is probably because the cancer cell is aggressive in nature. So once you occupy the bridgeport, you don't go there to feed yourself well to grow. You try to invade, you try to flank. So immediately this actually is not so much only for the supply of nutrient, but provide them the invading route. Okay, so this is one argument. But unfortunately, we're still not able to publish the work after 5 years. So we probably sacrificed 300 marks with 10 different cancer phenotypes and try to get this. And this is one of the results you can see. With one category of cancer cell, we can create all these called a solid tumor. You see very clear that you have the whole brain is much bigger like this, and then you can say this is our tumor. And an diffuse tumor like this, you can see that it was you don't see a tumor, but you can still detect them by looking at the alterations of the vessel. Some of the vessels become very irregular, very flat, and so on. So we can highlight them, identify. So these are the vessel being affected by these cancer. These cancer cells being the one migrating, they don't group together, become a solid mass. So they migrate through your vessel, and then when they find a place, they can sit, they start affecting your local environment. So this actually is the really pessimistic message of this is it's almost uncurable. Because you can see it's between these two models, it's actually can switch. So when you have a solid tumor, so you say, okay, I'm using anti-angiogenic drug or whatever, I try to kill it. And these cells mutate, becomes diffusing. And in the worst case in mouse, that they can infect 90% of your brain without killing. But then you know when 90% of your brain is infected, there's no way you can operate yourself. Okay, and then to high resolution work we want to see is how this particle, there's a thing called a blood-brain barrier. So because the brain is protected, so you cannot easily transmit things from the vessel to your brain tissue. That's why so it doesn't get infected. So now this is a very particular report saying the COVID-19 actually can affect your brain. And our collaborator, academician Johnson, say, yeah, it's through olfactory. So it means it's transneural. So when your neuron smells this and then the particle, it goes through a receptor, goes through the neuron, it passes through the cell because it cannot go through the vessel, which has been proved for many, many years. Virus, bacteria cannot go through the vessel. And what we do here is, but this vessel is a regular vessel. But if endogenous vessel, we know it's leaky. That's why the basis of nanomedicine to deliver nanoparticles to your tumor, that's the most significant application of nanomedicine, is based on you have a leaky vessel. So we want to try that. Unfortunately, this is not a successful example that just show you the image. We identify one vessel like this, and you can see the golden part is still our nanoparticle injected the tail vein. We want to see if anything leak out. Unfortunately, it doesn't look so. So it means even this vessel is about 10 micron in diameter, it's one of the smallest, but still it's not an angiogenic vessel. It still doesn't show the particle leakage. But anyway, so okay, what do we learn? Okay, this is about that. Conclude that part of the research. Of course, we want to use it because at the moment it's only for animals. If you want to apply to human, it's still a long way to go. Because, okay, but for animal, we say, okay, it can help us to do the drug development and so on. So this is the conclusion. But there are all when we are doing this, okay, even though I knew that neuron is one of the biggest things in all science, okay, brain. So, but then we can say, okay, what do we do with X-ray? Okay, the first question, can we image neuron? Okay, and we can image blood vessels, which we already know, and then can this X-ray then study neurovascular interaction, which if we can image neuron. So we started to try many years ago to image neuron. Start from the culture cell and then all the way to tissue and brain and so on. So, and then back to why brain. Why I'm always interested in brain, of course, its significance. Actually, it's the mysterious part of that. Now I was able to convince many physicists, including Li Dingguo, to be interested in brain. Okay. And even Chen Jiande院士, we try to trick him, say, everything about the supernatural is all in your brain. You have to study brain better. Okay. God, there's I think that many years ago, he said, okay, religion is in your brain. God is in your brain. It doesn't exist. But it looks so real because he created it. Okay. Okay, then what actually we think is a structural tool mainly. So we want to say, what can we do with that? And then so mapping the brain is one making most sense. Then indeed it's a historical mission. Okay. Now I encounter a lot of biologists telling me, they don't care about the structure. They're only interested in the function. And as a material scientist background, they know this is bullshit. Right? Because why you don't care about structure? Only because you don't have the structure. Right? So if you look at material science, the first thing they do is look at the X-ray and determine the structure, right? Like this new super high TC conductor, they don't even have that. So that's why we don't believe it. Okay, and so it is fundamental. So I would say a lot of resistances never consider this as doable. To get a complete map of a human brain. Okay, and then we start on this illusion. Okay, and then we say, okay, it is fundamental, and this is all the argument why we need that. Okay, which I think they know, they just don't want to admit. Okay, except you. Okay, I would say like An Xinjiang was one of the exceptional biologists. Okay, and the challenge, of course, so far there's nothing has a high enough speed and throughput. And then now you can say, oh, MRI can do that. You can look at the whole brain, but then you don't have the spatial resolution to do the structure. So now the connectome is dominated by MRI community, showing you, oh, you have information flow from here to here, give you all this wonderful, beautiful colored picture, but it doesn't correlate really to any fundamental structure because brain is made of neuron. So you have to at least know the neuron and how it's connected.
How about the radiation side, the dosage and the damage?
Oh, it's post-mortem, so we're not dealing with the live brain yet.
No, I was hoping you can get the video of the.
Yeah, we'll get the video. It's moving by camera. All right, so we propose this, and then the rest of the time until you stop me, I will just talk about this project, and hopefully that can inspire a new generation of physicists to believe in that there are things we can do. We don't need a biologist to tell us. Okay. Okay. This is effort. This is an effort to image neural network with the whole human brain. Okay, and with the proven performance. This project we tried because for a long time it's too good to be true. So you could tell every biologist, it's like it's not possible. So we have to use what we can do right now to show them. By calculation, it's doable. There's no extraction, no projection, okay? By synchrotron X-ray. So this is one of the major efforts we do in the last 2-3 years, is to convince first our synchrotron community that this is doable. And what we do is we want to do a collective effort. So the goal is this has to be delayed because this whole year is completely wasted. So we would probably say in 3 years at a time, we should be able to map one human brain. Okay, and then this is international effort, and then okay, so right now using our proven performance, that was 2 years ago. Okay, we calculate to map a human brain would take us 34 years. Okay. It's bad, but compared to millions here. So people say we want to do TEN and then ribbon cut your brain and then continuously feed it into TEN and then to get every neuron. And then that was An Xinjiang calculator with 17 million years for that. So compared to that, 34 years is excellent. And that's why we started saying, okay, if we have 34 years, that's one beamline. But synchrotron, like a new synchrotron, you can support 40 beamlines. So if we have 40, we improve it to No, 1 year.
You can occupy.
Yes, unfortunately that is the case. So we cannot even occupy one. By life, I try to fight for a beamline in a synchrotron, but the management always say, "You're doing it for yourself." No, we are supporting general users, so no, we're not going to support you with that. So the trick to go around is, okay, I talk to all my friends in the synchrotron, say, okay, well, can we form alliances and do this parallel thing? Okay, so parallel taking. And then the even more attractive part for these directors of other synchrotron is it's actually risk sharing. Right? So nobody can even put it several beamlines for you, even though this is, you can argue, hey, you got 40 beamline capability, now you have only 5. Why don't you leave me? But they will never do that. So basically, it's risk sharing. Everyone says, oh, this is small effort. If it doesn't work, it doesn't hurt me. And then, so they're happy to join. And of course, everything else has to be taken care of. But most important thing, which is actually, now, for example, we already see this problem. We have all the data. Our data accumulation is much, much faster than our processing. Okay, so I will mention a little bit of the problem later. Okay, so this is, and we believe this is a solution. And then through the last 2 years of effort, I was able to group all these synchrotrons. And then we targeted into, okay, the name is Synchrotron Vanilla, Asian Pacific Strategic Alliance Enterprise. And why Asian Pacific? Okay, first of all, I don't need to deal with jet lag if I go everywhere. No, the most important thing is, the reason is, we know we cannot collaborate with the US, right? Because there's no collaboration. If they want to do it, they do it. Same thing with China, right? If I put China in, I would tell the story later. And then Europe has their own brain project, human brain project. And then even though I know the person there, but I think it's better to start with this as our Asian Pacific initiative. And so these are the few synchrotrons, some of them, Wuhan, Spring A, Taiwan, Shanghai, and Australia. These are all qualified as a 3rd generation synchrotron, and they have even other newer upgrades. So the capacity-wise, this is, and the other trick is, so in January this year, we run our inauguration 四师大会, so in Singapore. So our director, synchrotron director, Singapore director, Korea director, and Japanese synchrotron director, and so on. And then we have 6 synchrotron. 4 of them showed in this meeting, and then we also have 4 supercomputing center. Singapore's national facility, and then Taiwan's high-performance computing center pledged to join. Okay, so and how much resource they can allocate, but at least it's the first step. Okay, I was very proud I was able to force them, to lure them to sit in one place to sign an MOU. Okay. And, yes, and then we got Nobel Prize here, Nobel Prize here. And, this is me. Yes. Okay, so this project, other than synchrotron, because we do want it to be a synchrotron initiative, because otherwise we have to deal with too much biologists. Okay. So we say we start with synchrotron, but we want to be a little bit broader. So we say we will incorporate all the 3D imaging tools. So the idea, the strategy is we give you a map, roadmap in a way. So like a Google map, it's very raw because we are targeting 0.3 micron optical resolution. So you are not going to be seeing synapse or fine connection. You are seeing the major track, major highway, super highway. And then so you require the other technique, as in functional molecular imaging and so on, to annotate or augment this structure. So it's like the Google Maps. When you go in, you start have street view and so on. So this will provide you a skeleton. So at least that makes sense for people to compare. So otherwise, you got a super resolution, you go to a specific site, not to draw up a mouse, for example. You do not even know where you're looking at. And then you do not know where you're comparing with others. So we give you a standard that you can do. So these are the list of the things we are confident we can implement it because we have our own cryo-EM facility and expertise, and we have a lot of experts like Professor Zhu Siwei giving us the optical microscopy information and so on. And so these are the plan. Okay. And in the synchrotron, we have already implemented our instrument and identical instrument into already 4 synchrotron facility. Okay. And in Taiwan, we actually have a robot. So in principle, we can close the hatch, and then we section the brain and put it in piece, and then can do more than a week without opening this hatch. So this is to show our calculation, because when we say 34 years is based on no downtime, no, just say calculate image one piece. Our speed at that time was 5 minutes per millimeter cube. That's what we demonstrate. We say you calculate by this, you get a 34 years by dividing the volume. Okay. But now the good news. This is supervised IAMS. This is our collaboration in this program with NB that we show super resolution using optical microscope, and then with tissue clearing supported by Anxin Qiang. So this is the movie to show. Okay. So this is the article published. And in X-ray, we published actually one article a few years ago. It's like this. It's not really, this is an invited article. It's not a real paper. But basically, you take the opportunity to outline how we're going to proceed with this strategy. Okay, basically the problem is, okay, when we do proof by brain, which I'll show right away, you can see the volume-wise, it's 8 orders of magnitude. And then the number of neurons is also a lot different. So when you can do Drosophila, has nothing to do with whether you can do mouse or not. And then when you do animal, then it's still far from that. Okay, you can see each one. These are about 2,000. This is 20,000 times. This is 2,000 times or bigger in size. So it means when a lot of people don't tell you they can do full mouse brain, few hours, few days, but then you can calculate, okay, by 2,000 times more for human, can you do that? Okay. So in our case, okay, this is Anxin Qiang in 2006. We first sort of announced this technique, our intention to map. So he was giving presidential lectures in the neuroscience SFM. And then later, Nature made a report, cover a lot of what he announced there, and they say, the biggest problem is the enormous amount of data. So we calculate based on our resolution. So you see, our resolution is 0.3 micron. And then we need to image with, say, 100 0.1 micron Boswell size. You calculate by this size, and the volume of the neuron and the brain. And then the data size, if we collect one human brain, will be about 1 exabyte of data, which is Taiwan's supercomputer center is probably total probably less than 50 petabytes. So it's enormous in this way. And then let alone analysis or every step is a problem. Everything we did in a routine way, like a tomography reconstruction, everything becomes a problem. Okay. So, for example, Anxin say, okay, he used his own example experience. He said Drosophila brain is 135,000 neurons, but it took him already more than 10 years to finish one half. So he would say, okay, it took him 20 years to finish this map. Okay, so by comparison, if you use do the same thing, the human brain would be this much of time. Yeah, okay. And also data size, now you can see that there's 36 petabytes is for 100 mouse brain. So then for human brain will be much bigger. So, okay, this is not show, this is just to show the resolution. Okay, and then the important thing of this X-ray is it provides you probably the wildest while there's the range of resolution and the coverage. So this is the previous two slides was trying to say that, and I will skip it. So you can see start from half a micron resolution all the way down to 20 nanometer resolution. You can get different levels of information. Start from a complete mouse head, this is with a skull, and then a piece of mouse brain, and then medium resolution and so on. So it's arguably one of the best tools for this task. Okay, so we have coded a name for this technique. It's called exon, and basically it's just two beam lines. So we see synapse and synapse and the neuron exon. So basically the two beam line. One is covered with a nanometer resolution, nanoscale resolution. The other is submicron resolution. So this one can be very fast, which will give us a whole brain image, and this one could allow us to zoom in any specific region you're interested with the supposedly projected 10 nanometer resolution. So that will be sufficient to see synaptic connection if you can label it. And then the nice thing about this is actually practically one same X-ray. So basically you can just put a sample from here to there. You know, we did not want to make it one beam line because that's a reduced efficiency or throughput, but it's relatively easy. So it gives you a very good way. Just if we look at one tomography, you say this specific region we're interested in, you can just move it to the next line immediately to do your high resolution work. So then the rest I was just showing continuous examples of what we have done. So this is start with the Drosophila, which is done 2016. And this is how we get Jiang Shiyuan is all excited because this is include a whole head. We're imaging this, and now we can do this within 1 minute, the one complete scan. So as I said before, our parameter is 1 millimeter cube by 5 minutes. But now we are achieving it by 1 millimeter cube for 1 minute. So it's already 5 times. So instead of 34 years, we think we can do it now within 3-4 years. Okay. And so these are the individual neurons that you're saying. And then the colored one are which they catched from their database. So that was the reason I started with Drosophila, because we really don't need to do this because Anshin Jiang using optical tool is already doing very well. So the reason we do X-ray is really for the comparison. I can tell the other competitors say, yeah, you do this, but you don't know what you're doing. We have a map. We have already a partial map that we can fish them and identify them. Okay. So this is an idea that we are merging different brains because one of the tricky part didn't tell you, okay, one human brain doesn't make a connector because we're staining only up to 5% of the neuron. So it may not even form a network. And why do we want to do that? You know, just because it's human brain. Mm-hmm. Okay. And I was given a talk before, like our physicist talk, I say, frankly, I really don't know what this is for. And this, as a Nobel Prize, Bob Laser, he was in Taiwan last year. So he was saying, we were there to celebrate the human landing on moon 50 years anniversary. So he said, yeah, look at what do we get out of landing the moon? Nothing, just prove we can do it. Right? And so he said, yes, exactly the same thing. You prove we can handle human brain. So now you need probably hundreds of human brain to complete a map because this is the idea. Drosophila is the same. We stain only 3% of the brain, but we have 500 set of data. So by morphing them together, same idea that Anshin Jiang proposed, now we should be able to give you not a specific, precise road map, but rather a statistical sense, which is meaningful because brains are not the same. Even Drosophila, you can see the size, the shape, it's all completely different. So by morphing them together, building a standard brain, that you can have at least a statistical sense about how they're connected. So this is the idea, but then with the improvement, now we say we are improving already 10 times, and we believe with the new instrument that we get, or new technique we invented, that we will be able to get another 1 or 2 order magnitude faster. So in principle, we can do 1 millimeter cube within 1 second. So the human brain is 1 million millimeter cube. So you can say, okay, 1 million seconds, I can add 1 human brain. And then we can also track, label specific neuron, one neuron in this case, and still imaged by X-ray. But I would not pay attention. This is only interest for biologists. They always want to see what they label. So far, they cannot comprehend, say, I give you a randomly identified, and you sort it out for me. They say, okay, for 2 decades after the inventions of fluorescent dye, the whole doctrines of biology becomes, I label, I want to see what I label. Okay. So that was, but yes, we can do that. Unfortunately, that has nothing, it doesn't help at all of the brain mapping. Because I'm not going to do one neuron at a time.
So that's labeled on the neuron on the top. But how about the circle?
Here?
Yeah.
Oh, these are, every label they have, debris and so on. And then these are labeled as much brighter. And for example, all these are natural contrast, maybe something stained. That's a major problem is this specific stain. It's not specific. They always tell you, oh, this protein binding. So one time you say, okay, I send an antibody to label one specific protein. And you don't ask the question, so are they effectively, so we have stained a lot of time with, for tissue, it doesn't penetrate, right? So you see it stain everything outside except what you want to stain. But when they look at the cell biology, look at a culture dish, there's no problem like that. When you start making a tissue, so when they use a genetic transfection, which is much better, but if you use external labeling, it's always a problem. So here, they use a genetic transfection too. They transfect a neuron into a specific protein expressed by this specific neuron, and then using some kind of enzyme to metallize these outside. So, okay, so I think these are just some images to show. This is a high-resolution work of one specific neuron. This is, I would claim, a 20 nanometer resolution. This is 1 Purkinje cell. You can then actually see this little dendritic splines stick out, which is related to synapse. Okay, this is a whole mouse brain, but I used the trick. I did not do the 3-dimensional image. I just used one projection. But the vessel image is 3-dimensional, just to show that, yeah, indeed this will look like this if we are able to stain neuron and the cell. And this is one slice without tomography. Then you say, why don't you do tomography? The question is, each one is our tomography volume. And then this is by power of 3. So if I want to do the whole volume, I have to do 30 by 30 by 30 tomography. Okay, which right now our throughput is not high enough for that. But it's coming there. Okay, so these are all the images of different levels of neuron. Okay, speed. Oh, sorry, 1 hour. Okay, I will show you this movie and then conclude the talk. Okay, I think I'm done.
A question.
Yes.
Any improvement in the detection side will help.
Yeah, this is always, that's why.
So you can think of the other side, which can shorten your reconstruction time, collect more
Yes, that was why actually I had a long time trying to collaborate with Li Sichang. Yeah, trying to, and he's helpful. He's very wanted to help to build a new detector for us. But again, this is not a easy business.
Sure.
Yeah, so you see, I didn't tell you the thing I'm proud mostly is, all these big operations, it was not supported. It's not funded by anybody. So we're using our own individual funding and to do this work and trying to. So fortunately, when we have the inauguration, we made a last few minutes phone call to the ministry, and the minister decided to give us at least some coverage. So they wrote a newsletter, put it in their website, and say they're interested. Okay. And even more discouraging is academia sinica doesn't pay anything. Yeah. Okay. So these are just one piece of the bow spring. And then each different color is, I try to connect them. So these are the neurons, likely connected. So I give them one color, and I keep adding up. So this is one very small piece. This is 600 micron in diameter, and this is the remaining. So if I put everything together, you cannot see anything. Okay, but these are the real. Even this looks like background. These are real connections. Okay. So how do we extract information from this? Is a big challenge. Okay, so in technical imaging side, as I said, I'm as confident as anybody question that, I will be very angry. So, but again, the real at the end, can we get information out of that? So that was actually why I was asking for help, and then this is what this Nobel earned. And then she said, yeah, he said, yes, that's that actually relieved us. So because you see our claim in this 20th, we'll give you the data. Okay, I'm not promising you information. I'm not promising you that we can cure the Alzheimer or something like that. But this is really the first step. And unfortunately, we are still. That's why this year we're supposed to try to go very active to ask for funding, not from our government, but for example to do the algorithm for this all the treatment. And our advisor also suggests the best way is crowdsourcing. Because even if you have money to hire 100 programmers, doesn't guarantee you to get anything. So the best way is put out the price, and then the internet hackers and hackers or the students to compete. Okay. And again, that cannot be supported by government. Government, you cannot use government money to say, okay, I set up a price. So that was something. As I said, we are also thinking about these wealthy alumni. Unfortunately, they are too practical. All right. Any other questions? I will do my own.
Any question?
Yeah. So that's very interesting talk. Say, is that possible? Can you make the dynamic mapping? Because that's, I think that's very important, because it's very difficult to let our brain stop. Our brain always thinks something. Yeah. So probably in the future, maybe long time after, say maybe some people will be able to mapping the brain and read what you are thinking. That would be very interesting.
No, we actually had a project not to know what you're thinking, to try to make you think. With John Hansen. John Hansen successfully do that. The community successfully do that to control the motion of fly, Drosophila. So basically, they use this technique called optogenetics. They coded a specific protein into a specific neuron, and then by activating by light, okay, this is optogenetic, and then they can either stop this neuron, truncate its signal flow, and so on, and then it will behave in a specific way. For example, he claimed that I saw that. So if you shine a laser, this specific Drosophila fly will jump, will make a right turn, left turn, or even turn them from homosexual to heterosexual. That's very politically incorrect. Means that it's correctable. Anyway, so then we can see that I argue with him is, okay, you're using optical light. Then you cannot do anything with animals or human, okay, unless you poke up of them. Okay. So we had this idea since 15 years ago. Say, okay, then we use X-ray. So it turns out X-ray doesn't activate any of these kind of protein other than damaging it. So the only way is to put in these scintillators. So we are trying to develop this scintillating nanoparticle. So if we can do this, and then we can bind that with this specific protein like channel rhodopsin, and then by the X-ray, because this is so close, right? So the efficiency is much less a problem. So you have a little, we call it internal light bulb. So you have this internal light bulb next to that, and you shine X-ray. So ideally, so this project was a proposal now with the U.S. Air Force. So you can see what they have in mind. Yes. So, but this is a long shot. Okay. In terms of imaging, yeah, I think everything reaches the limit. I think if we have our medical development for X-ray is promised as delivered as we promised, yeah, then you have better resolution. But everything else medical, you can assume is completely optimized. So it means if they cannot give you anything better, it's because it's damaging X-ray. So we're fighting to say the argument is using the same radiation dose, because of phase contrast, we can give you much more information. But in terms of the brain, it's hopeless because it's a piece of tofu. If you look at that, so if we don't stain it, you don't see anything. Okay, but when we stain, that's why we have to do only post-mortem. So in our inauguration meeting, as a 事大会, we were very tempted to give letter to everyone to sign to play my brain. But then yes, we said, hey, if Einstein donated, okay, you can compare how dumb you are. But then at the end, we didn't do that because Singapore, it turns out, is much more conservative than Taiwan. They said they are really traditional Chinese community, very treasure their bodies. So they said that NUS hospital doesn't even get the cadaver for student anymore because nobody wants to donate. And so they have to buy from India, probably, or China. Yeah, we can, the brain is a major issue now because so we are working with several hospitals trying to make it, because you cannot use organ donation, because that's only for saving lives, so not for research. So if you want to get anyone specific right to donate their brain to research, it's okay, but then he has to die right away. Right? We have no, you have no idea. Yes, so that is the major problem. All right.
Anyone?
Good. I promise I did not give any equations.
Oh, I think it's time is up. Yeah. If not, let's thank Dr. Hwu again.